Hello and welcome. In this lecture, we will learn how to perform simple linear regression using Python. So in our previous lectures, we learned the basics of simple linear regression and then how to perform that using manual steps. Now let's quickly understand how can we perform that in Jupyter Notes and what are the basic things we will need to do even before starting off your regression. So first is pre-processing. You have to pre-process your data, and then then you move on to simple linear regression. Okay, so first we need to get required libraries for regression. The first part is pre-processing. So let me write it as pre-processing libraries. So the first library will be of course it will be pandas. So I'll import pandas as PD, then import numpy. Then we need something called as statistics to perform all your basic statistics. So we will import statistics. Now which are the other one? Okay, so for visualization we will need import matplotlib. We will learn more on that. Matplotlib dot pyplot as plt. So matplotlib is basically the library which helps you in visualization to build your box plots, scatter plots and all. We have discussed that, so we will need that. The next one, yes, if you require some sort of a scalars, let's keep that also ready. That is in sklearn. So we will have sklearn dot model underscore selection import it should be from from train test split. So this is for sure you will need it. It is, and then if you want you can also get your from sklearn your scalars ready, feature scaling from, if it is required, from sklearn dot pre-processing import min max scalar. This also from sklearn dot pre-processing import standard scalar. That is when your distribution follows a normal distribution, you can use it. So that is pretty much of it in pre-processing. Now let's talk about libraries required for regression. One thing I want to tell you is that we may need a few more libraries. We will import those libraries when it comes to that point. Okay, so for now these are the basic libraries we will need. We will start off with that and then let's see what are the other things we need. Okay, so then we need linear regression. So we will get it from sklearn again, from sklearn dot model dot linear model learn, sklearn dot linear model import linear regression. So that's done. Then we need something called a stat models. Import stat models dot API as SM. So stat models basically will help you to perform ordinary least squared regression in a different, this is a different library available for ordinary least square regression. If required, we can try that also to see if the model is improving by any chance. That is fine. And again from sklearn metrics, from sklearn dot metrics import two things. One is a mean squared error, and then obviously you will need your R square as well. So R square. So these are the library from sklearn dot metrics you need. That is fine. So one more thing from statistics, just to be on the safer side. So from Skippy import stats. This is also a very good library for basic statistics. So in case if we need it, we keep all these things ready, and then it is easier for us, isn't it? Okay, so let's run this. Let's see whether we have typed all of these things right. So what's the problem? No modules, matplot, oh, matplotlib. It is not matplotlib. matplotlib. Yeah. So that the next problem is sklearn, Learn. Learn. Which line? 7th line. 1, 2, 3, 4, 5, 6, 7. Learn. Learn. That's important. We spell it right. Stat models. Stats models. Stats models. Yes. How the issues are solved. Yes. So we got all the libraries. So just pay attention to type it properly. So that you will not get errors like this, and it is easier for you. So it is important that we have a little bit of focus while typing. All right, now let's get our data set. The data set we are going to use here is salary data set. I will share the data in the resources section, and this is basically to run a regression on your experience versus salary. So your X, we are treating that as experience in years, and your Y you're treating as salary what you earn. So you want to model these two variables. By using experience in years, we would want to predict what would be my salary. Okay, so this is a very good and an easy and a simple example. The reason why we are taking it, because we have already spoken about it in our previous lecture, and plus it is easy, okay, for you to understand, a simple one. Okay, so let's get the data first. I'm going to call that as data. Data is equal to pd dot read CSV file. It's a CSV file, and then salary. This is how it is stored, data dot CSV. Shift and enter. So the data is there. So if you want to have a feel of the data, data.head, you have the data ready. You have experience, years of experience, and salary. Okay. So the first thing what you need to do now is to quickly check for any missing values, because you need to ensure that there are no missing values, isn't it? So what is it we do? So we will say data dot is null dot sum. If it is null, you give me the sum of it. Fortunately, it's an easy data set. There are no missing values. It's all the values are present. It's absolutely fine. So if you want to know what is the dimension of it, you just need to type, you remember, data dot shape, and that is 30 rows you have and 2 columns. 30 rows of data and 2 columns. So that's absolutely fine. So what is the next step? So first you check whether there are any missing values. Fortunately, there are no missing values, so you don't really need to go behind that. And the second thing what you can also possibly do here is the scaling. So although when we discussed on feature scaling, we said scaling is typically done when there are distances to be calculated. Here there are no distances as such we are calculating. What we can do is we can run it without scaling and see what is the efficiency or what is the accuracy scores, R squares we are getting, and we will if required, if we are not very happy with that, we will scale the data and see if there is a change. Okay, so for now let's not perform scaling. Let's straight away go into calling up your x and y's. So your x here is years of experience and y is salary. So I can very well say that my y is equal to data dot y is salary. So salary, data dot salary. I can even write it like this, data dot salary. So that's done. So but data dot salary, it is basically a data frame now. So if you want to create as an array, you remember, just put it as values. So I'll just put this as extracting x and y from the data set. Okay, so x, y is done. Now you need x. So x you have, so again it is from data. And what is x you are looking at? Years of experience, years experience. Very quickly, years of experience dot values. So just to jog your memory, you could do it with dot iloc, simple iloc, and in this way also. So it's very simple that way. Okay, shift and enter. So your x and y are done. So if you want to quickly check what is your x, that's an array like this, and y, it's another array like this. So that's fine. You wanted to share it, save it as, store it as arrays. So you did your dot values. It's done. Okay. Now you have done your x and y. Now you need to split your data set into training data and test data. We discussed about this, so you must be aware of that. So first we will call our data names. So we'll say that it is x train, x test, comma, all separated with commas. And then we call it as y train, y test. This is what we want. And we what is the library we have imported and kept? You can come and copy paste this. You do not want to make any mistakes. We'll say that this is the library, and in the order, first please take it from my x, and the second one, y train and y test, please take it from y, and then the test size is around 30%. You can easily give that. And then random state, where do you want to start randomly? Selection of the samples, random state, maybe start from the 20th row. So we'll say put it as 20, random state that. And shift and enter. Let's hope that it works. Yes, it worked. So your x train is prepared, x test is prepared, y train is prepared, y test is prepared. So your data preparation is almost done. Okay. So now if you want to, before we split this data, there are a few things what you will need to ensure if you want to continue with regression. The first condition, if you remember, is that there should be a linear relationship between your x and y, and that you need to prove first. Okay, so two ways you can prove it. One is a visual way of creating a scatter plot, and the other one is called as Pearson's correlation coefficient. So let's start off with the scatter plot. Scatter plot is within x and y. You are trying to see if there is a relationship between your x and y linearly or not. So scatter plot will help you to do that. Let's find out how will that help you. Okay, so first one is, so for scatter plot we have already imported the visualization tool and kept. So all you need to do is you can say PLT, that is use matplotlib dot scatter, and scatter between what? You want to check between your x and y. Okay, so PLT plot scatter plot for me, and the variables I want to check are x and y, and shift and enter. So you see that this is your x and this is your y, you know that. So if there is a kind of a linear relationship, this will be like this, where as your number of years of experience increases, your salary increases as well. So that's basically what is shown here. they don't follow a straight line, but by and large it shows that it is linearly related. That is important, guys. Okay, so this is a visual. So create scatter plot, and now you can also mathematically, if you want to check, you can perform correlation. So how do you perform correlation? You can go two ways. So you can either use your NumPy basically to do correlation, or there is another library called Pearsoner. That also can be used for your correlation checking. So let's first use NumPy, and then we will use the other one. Okay, so first I'm going to use NumPy. So we'll say NumPy np dot correlation coefficient. That's how you write CORF, and then correlation between what? You want to do a correlation between your x and y. Okay, so what is correlation coefficient? So scatter plot gives you a visual understanding in terms of the relationship what they share, whether they share a positive relationship or negative relationship or no relationship. So if it is a straight line sort of a relationship where you can feel that your data points are linearly related, that is visually proven now. So to get some mathematical conviction, we do this correlation coefficient. There are different correlation coefficients available, but we generally we are going to discuss here is Pearson's correlation coefficient, and that correlation coefficient shows you the strength of relationship between your x and y, how much it is correlated. So it is a ratio which ranges from -1 to 1. -1, if the ratio is the number is showing as -1, that means there is a negative correlation. That means one increases, the other decreases. In this case, it's a positive correlation. One increases, other also increase. So it should be a positive value. So the positive value, the strongest relationship, if it is so tight, then it will give you a correlation coefficient of 1. Basically, minimum we need a correlation coefficient of more than 90 to accept that as a strong correlation and then proceed with regression. So now let's see what is the kind of correlation coefficient of an array. So in a form of an array it is given. So this is correlation coefficient 1 is between x and x itself. When they are taking x and x and try to make a correlation, it's basically they are making into a 2x2 row and column. That is the reason. So x and x, when they are studying correlation, it is 100% correlation. Obviously, if you have the same variable and if you try to correlate it with the same variable, it definitely will have 100% correlation. And this is when x is correlated, how x is taken as first variable and y is taken as first variable. You see it is 90.9782, which is a very strong positive correlation, because there is a positive sign, there is no negative sign, that means it's positive sign, and is very high, and a high correlation is shown here, 0.97. So whatever more than 0.90, we consider that as a very strong correlation, either greater than 0.90 negative or 0.90 positive. So here it is positive. So it is a strongly positively correlated variables, and it is 97%, 97, and this can be very well be qualified to be used for a regression analysis. So that basic correlation, perform correlation to determine the strength of relationship. Okay, and scatter plot is used to visualize the relationship. Okay, so that is done. So we are kind of technically through to go with regression. See, one thing we had to validate before starting regression is, the first thing is basically this one, that there is positively correlated. And if you remember, the remaining part of the assumptions will come after we complete the regression, because you are mostly going to talk about the errors, the residuals. So residuals can be got only once you have your prediction done, because prediction value minus the original value will give you the residual. So we will have to wait till that point. So we will run the regression and then we will validate the remaining assumptions. Only those when these assumptions are true, we can use this model for further production use for forecasting or prediction. Okay, so now that's fine. Now let's quickly get into the regression. We are going to perform regression here. So regression, we have already created the library. We have this library here. So we will take that and we create that function and keep it ready. We say that linear regression, you can put any name you want. I'm putting it as linear regression. And then, so whenever I want to call this function, I just need to type ln. Okay, so I'll run this and I'll keep that ready. Now the first step is to run this linear regression. So if you want to make a name, you can create a variable also, you can keep it. Say if you want to name this as, say, salary, SAL, you just keep it as salary and say that, okay, now ln, please fit ln dot fit your xtrain. That's your first variable, isn't it? You fit a regression model for xtrain and ytrain, because those are the two variables what you have, isn't it? Xtrain and ytrain for me. So fit that and store it in sal is what you're saying. Shift and enter. Train, Train, Train. Shift enter. So let's see what is a, oh, okay, there is an error. Expected a 2D array, got a 1D array. Okay, this was expected. So what, guys, what we have done here is, when we are talking about x, we have converted xtrain already into an array. So if you type that xtrain dot shape, xtrain dot shape is giving you 21 rows are there, because 30% is what we called, right, for testing. So 7 multiplied by 30 is about 21. 21 has been reserved for your training purpose. So, but here the problem is that I have got 21 array, 21 rows, but there is no mention about the columns. So since there is no mention about the columns, it's actually considered as a one-dimensional data. So here if you see that, it is expecting a two-dimensional data, but we gave a one-dimensional array, and that is true, we gave a one-dimensional array. So we need to change it. How do we change it? And if you also want to know what is the dimension, you can always type this, right, xtrain dot ndim. Just need to type ndim and you see that it is a one-dimensional data, but we need two-dimensional. So if I call xtrain, how that xtrain will look like, let's have a look at it. The xtrain we call, see, it is typically showing as a row, a single row, where it is kind of a list and it is in an array which is showing. We want this to be multiple rows of 21 rows, and then those one column that has to be established. So what we do is, we have a formula or a function called as reshape. So we can do is, what we'll do is, we take this and we say dot reshape this for me, and now reshape, and now what I want to do is retain -1. I'm giving -1. What I'm saying is that retain all the elements and convert that into rows, and then add one more dimension, which is a column dimension. So -1 states that please keep all the values there and make that those are existing values as rows, and then this one shows that it will please make it to column. So this is what we can even call this as xtrain now. So xtrain is equal to xtrain dot reshape, keep this entire thing and reduce that into one multiple rows of 21, whatever, how many of our elements are there, convert that as rows, and comma 1 shows that create another dimension of a column. Let's see what's happening here. So shift and enter. Now if we call for xtrain.shape, you will see that there is a difference. See, it is showing us 21 1. And if you want to see what is the dimension, you see that if you type dot n dimensions, it is showing us 2. So that is taken care now. So it is a two-dimensional thing. And if you want to see what is your xtrain, you will see the difference now. What has happened to your xtrain? Shift enter. See, it has created rows. So it has 21 rows. Whereas here it was like a single row, you have put in all the numbers. And then obviously I have to change my Y train also, because again it will be a problem when I try to run it without changing. So what I will do is I'll just do the same thing to my Y train also. I'll say Y train is equal to Y train dot reshape it for me, please, and keep all the rows as all the elements as those many rows, and then introduce one column for me. So that is also taken care. Reshape, RESHAPE, reshape. So that's also done, I think. Yes, it is done. So let's quickly check on the dimension of Y train now. Y train dot endem. Yeah, that's a two-dimensional. It's created a two-dimensional thing. Now let's run this. I hope that it should work. Yes, it worked. So when we reshaped it, that error is gone, and then we ran it. It is perfect now. So if you call SAL, it will show that it is a linear regression model which is stored in here. So far, so good. Okay. Before predicting it, we can very quickly check what is the intercept and slope value. I would like to show you that first. So SAL dot intercept. You just need to type this intercept. Okay, SAL dot intercept, and just hyphen here, shift and enter. This is going to give you the intercept. So you remember what is the intercept? You remember the intercept? Intercept is when x is equal to 0, what will be the y value? Okay, so I'll just write it here. Check the intercept. Intercept is value of y when x is equal to 0. Okay, so that is done. Now what is required? Yes, we need the slope, isn't it? So check slope. Check the slope, just to have a good idea. So what we will do is we'll say SAL dot coefficient. Please give me the coefficient of this. Coefficient 1f is 1f. So this is nothing but the slope. Okay. So when you are taking SAL and say that please let me know what is the coefficient, 9622 is the slope. So that's pretty understandable now. So what is your slope? Slope is the ratio between your y rise over run. So when a unit change in your x, which is a unit change in your number of years of experience, there is an increase in salary of 9622. That means 9622. Okay, so far so good. So we know what is the intercept and what is the slope. Now let's go ahead and do complete our prediction. So how do we do that? We'll say that SAL has been reserved as the linear regression function which is stored in there. So SAL dot predict. Okay, SAL dot predict what? You want to predict for your X test. So far you have used only your X train. So you are going to do the prediction here. Predict the value. Okay, predict the value. So predict the SAL dot predict. What are you going to predict? So you are going to predict for the X test. Okay, shift and enter. So we're asking sal.predict, and you can even call this as your y predict. You're saving this as y predict, or y pred, you can call y pred is equal to sal.predict with x test, and shift and enter. X test is not defined. Oh, x is small. X test. Oh, then what is the error? Oh, the similar error, because it is one dimensional. We needed two dimensional. So what do? So we can do two things here. We can even directly give it here, saying that please do a reshape here. We can like something like reshape dot reshape and -1 and 1. You can do that, or if you want to change it in x text itself, what we can do is, we can just remove this, and then we can even insert something here and say that x test is equal to x test dot reshape it, make it into rows, whatever number of elements, and then create one column for me. X test dot reshape. That's done, and let's run this. So ypred is done. So if you are eager to see what is the ypred value, you just copy and paste here ypred. So these are the predicted value for the x text. Brilliant. Now the first activity to see how good is my r square value, because we want to know what is our r square value. We are not interested in your r adjusted, because r adjusted is for multiple regression, because there are the p value of p is only 1 here, so you don't really need to do that. So let's quickly look at what is our r score. So what is required for r score? The library, we have already kept it ready here, isn't it? So now what we need is, we will say please do r square score for what? R square, we can even call this as r square. If you want to name this as a variable, you can very well do that. You say that r square is equal to, between what? R square has to be calculated between your y test and your y predict, isn't it? Because you have both the values now, y test and y predict. You remember that xy diagram we did yesterday, where you will have your predicted values and you will have your original values. Your y test is nothing but your original values, isn't it? And ypred is the value which you have predicted with your simple linear regression. Now let's say shift and enter. So r square is already stored in it. So we'll say print r square for me. Oh, it's brilliant. 96.25 or 0.96 is the r square value, which is pretty good, isn't it? It is very good. It is very good. Okay. And now we are also interested in knowing our mean square value, mean sum of squares value. So let's take that also from this library. We have kept the library ready here. So we will use the mean square value. Okay. Let's get the mean square value. Mean square value, MSC, we can, if you want to call it some names, you can call it as MSC, is equal to mean squared error of what? The same thing. I need to y test, and I need a ypred, isn't it? Shift and enter. So your MSC is also done. So print MSC, that is 31,885,663. This is your mean sum of squared errors. That means you have calculated the error difference between your predicted and your original value, taken the difference, squared it, and divided it with the number of your samples, and that is this particular value. Okay, so that's also very clear. Now you have all the statistics what you needed. You know what is the R-square value, what is the MSE. You also know what is the coefficient and what is your slope and your intercept. All these information you have got it. You have got it ready. Now let's quickly perform the assumptions validation. The first and the foremost thing what we spoke about is that your error values should not be correlated. It should be random. It should not have any relationship between your values, isn't it? So your error values is something what you really need to check for randomness. So one way to check that for randomness is to check whether it is basically following a normal distribution or not. So a normality test is something what we are planning to do. Before that, you can even do a quick histogram and see whether it is following a normal distribution also. But here you haven't really gotten your residual values. Have you gotten it? You have not got it yet, right? So we can easily calculate the residual values and keep that residual values ready for now. Okay, calculate residuals. So residuals, maybe we can call it as residuals is equal to, it's basically, we know it's the difference between your y predicted and your y test. That's basically your residual, isn't it? Y pred minus y test. This is your residuals. This is your error component, isn't it? So we'll convert those y test into a two-dimensional array like this. So how do I do it? Y test dot reshape minus 1 and 1. So we'll say dot reshape and I'll call it as y test. That's perfect. Please subtract my y pred minus y test. Simple as that. And I'll call residuals. So we'll see that the residuals are perfect. The residuals are perfect. So first thing what I want to check whether the histogram of this I can probably do first is create histogram. So histogram is a good option for me. So I'll just say PLT, that's matplotlib.histogram, and what I need the histogram is of the residuals. If I do this, I'm not sure whether, I'm not convinced that this is fully following a normal distribution. I can't say that. So I'll need to do some sort of a normality test. Whether it is following a normal distribution, I don't know. So I need to do a normality test here. Normality test. So you need to, this is also sort of a hypothesis testing. What normality test is doing is, it creates two hypotheses saying that your distribution, the data set follows a normal distribution, and your alternate hypothesis is it does not. Your data set does not follow a normal distribution. So here, these two are your hypotheses. So this is what your null hypothesis is. This is called as your null hypothesis. Null hypothesis is the data follows a normal distribution. By default, it is like a judicial system. A person is considered as innocent until he is proven guilty. So until you have some evidence and you can prove that he is guilty, during the course of trial, that man is just an innocent person. So similarly, in hypothesis testing, until you prove that it is not normal, you believe that it is normal. So you need to bring in some proof and prove your alternate hypothesis that your data is not normal. If you cannot prove that data is not normal, I will consider my data has a normal distribution. To find out, to perform this test, we have something called as an Anderson-Darling test. So we have a couple of tests available. So let's first try and do Shapiro test. You have one test, Shapiro, and this is the name of the test, Shapiro test. Or you have another test which is called as an Anderson-Darling test. Anderson. So either of this can be used. It is absolutely fine. It's up to your choice. Shapiro is much easier to understand. So we can do it Shapiro. We can perform that normality test with Shapiro. So here for Shapiro to work, we have already created the library and kept, which is a stats library. It is Skippy. From Skippy, we have downloaded or imported the stats library and we have kept that ready. We will use that. So it is very simple. So normality test, if you are doing, you just need to call stats, that is which is from Skippy. So you'll say stats dot Shapiro test. Please do that Shapiro test for me. And Shapiro test on, it is on the residuals, because residuals you have kept it ready. So shift and enter. It's going to give you two statistics. This is a critical value statistics and this is p-value. So for your understanding, I'll explain to you what is a critical statistic. A critical statistics is a value which is called as a cutoff value. If the calculated statistics, we don't really need to go into the details of it now, but understand that this is the critical statistics. This is the value which I need to watch out for. And a similar value I calculate using my data points. If that value is lesser than this value, I will go ahead with my null hypothesis. That means the data is normal. And if that value is more than this particular value, I will go with my alternate hypothesis. But I'm not calculating that value. Instead of that, I'm getting another value called as p-value. So p-value shows that this is a sort of a risk indicator. Okay. So the p-value shows that if you reject your null hypothesis and if you go with your alternate hypothesis, this is the amount of risk what you will be taking in that decision. So this is also called as p-value. 14% is also, we can read this as. Okay. So if I am rejecting the null hypothesis, saying that my distribution is not normal, saying that my normal distribution hypothesis I'm rejecting, and I'm accepting that yes, the data is not normal, this particular value of risk should not be more than 5%. If that risk is more than 5%, I will not take any risk by rejecting my null hypothesis. I will always go with my null hypothesis. But in this case, the risk is 14%. When I reject my null hypothesis, the risk what I am taking in my sound decision that I could be wrong is 14%. So I don't want to take any risk. So I will take no decision. I'll say that I will go with my H0 because this is by default. Until proven guilty, that person is innocent. So I'm saying that I couldn't prove, because if I have to prove, I'm only willing to take a risk of about 5%. But as per the p-value, the risk is about 14%. So I'm not willing to take that risk. So hence I cannot prove him guilty. So before I prove him guilty, he was always innocent. Since I'm not able to prove anything against him, he walks scot-free. And walking scot-free is nothing, just going with your null hypothesis. So I'm going with my null hypothesis and I'm saying that my data follows a normal distribution. It's because of the lower number of data points, this distribution or a histogram is not giving you that kind of a picture. But since it was not giving you that clear picture, this is where we use the Shapiro test. Now let's quickly run the Anderson-Darling test also for your reference. So I'll do it in the same way. I'll call it from stats only, stats.Anderson and Anderson. And then I want to do it for my residuals. But here, before running residuals, because if you see what is your residual basically is a two-dimensional data where you have these many rows and one column is already defined. So when it comes to Anderson-Darling test, I want a flattened array. That means sort of a single row. So I can use my reshape here. I'll use my reshape. I'll say that residuals, please convert residuals dot reshape and flatten it for me, -1. Flatten it. I do not want column, comma ones I do not want. Flatten it, don't put another dimension to it. And then if I run my residual, if you want to check what is your residual now, you see that it will be a flattened array. The flattened array. Okay. So stats.andersons.residual, I shift enter. You see that there is a test statistic here, and these are the critical values. These are the critical values for each and every risk or alpha value I've set. So let me explain it from you. So it starts from 1%, the lowest. If you are ready to take 1% of the risk, this is going to be your critical value. So the value what you are calculating as a critical value at 1% is this, and your test statistic, as I told you, should be more than that for you to reject your null hypothesis. To reject your null hypothesis means say that your data is not normal, it is not normal. This particular test statistic should be greater than this, but unfortunately in this case it is not. So you can't reject your null hypothesis, you have to accept. It's a wrong usage, it's not unfortunately. Factually you can't do it. So your data is a normal data now. Okay. So if you are ready to take 2.5% risk, then the critical value is 0.808. So that 0.808 is also this value of statistics what you have measured is also lesser than this value. So you can't reject your null hypothesis. Still it is normal. Likewise it is for 5%. So Shapiro test was for 5%. So that is by default it is done for 5% only. Anderson-Darling gives you a combination or an option starting from 1% to 15%. So in 15% also, if you look at it, it's 0.507, which is still higher than this particular value. So that means I cannot reject my null hypothesis. And Anderson-Darling test also says that my data is a normal data. Okay. So I will give you more examples. This was a very simple and plain regression, but do practice this. I'm giving you this. Plus I'll give you an additional data sheet there, slightly complex. Please do practice that. And try to run the entire sequence of things what we have learned in simple linear regression and see if you are able to predict values. Okay. All right, then I shall see you in the next lecture. Bye for now.